So hello everyone, and nice to see everyone again today. And today we'll be working on another science case, which is actually creating a catalog, okay? Creating a catalog from an image, doing photometry. So before that, I'd like to just pause. Does anybody have any questions about yesterday's session? Are there any questions? You can anyway keep them on the chat, and we can handle them later on also. But Urvashi says she's have problem in replacing the column in mod thing. Can you help me with this? So I'll just share my screen, right? And let me share my complete desktop. I hope you all can see my screen. Yeah. So if you see my screen over here, this is the TopCat folder. So if there's any file which you have, right, you'll open the table thing. And then if you want to replace the column, right, all you need to do is in this column part, right click and put, right, say you want to, if you replace the column, it will overwrite the column. Otherwise, you can actually say new synthetic column, right? And your new synthetic column can be, for example, new. But now here you have to use the name of the column, right? That is there over here. So you will have to stick to this name, whatever it is. Unfortunately, I've taken something which has more complicated columns. So I'll just take another column, another file which has simpler columns. Yeah. So here maybe this one has slightly simpler columns. Okay, so there's number, for example. So I can right click, I'll say new synthetic column, and I can say num2, right? And supposing here, if I want to make it, I can say you add the expression. So I can say number into 2, for example. I'm multiplying each of these numbers into 2, right? And then I say okay. And here you can see this new column which has come up, it's num2, which is double of the num1 column, right? Yeah, I have already sent the PPT through email in PDF format. I hope you have received it. If you have not, you can inform me, but I sent it yesterday as well as today. Today morning also I resent it with the recording as well as I sent it yesterday. So Bala, if you don't receive it, please let me know. Okay. So we can take this things later and I hope you can see my screen, right? You can see my complete screen. Okay, very good. So today we are going to do something slightly different, which is we are going to actually talk about photometry. Okay. Now, what is photometry? Photometry is basically the measuring of photons. So what you see is what I'm going to show you today is we talk about clusters. This is a globular cluster using SDSS data. SDSS is the Sloan Digital Sky Survey. And this is a globular cluster called HGC 5466, which you can see over here on the right. And what I'm basically going to show you is that if you have an image of this kind, how do you create a catalog, right? What is a catalog? A catalog means you make a list where you have array decks of every star with their brightness, maybe error in brightness, and other such parameters for each star, right? And so we are going to make such a catalog using this image. So today I will show it to you using SDSS data where we will make this. I will also show you how to do it, for example, with HST data. HST is Hubble Space Telescope. And in principle, you can use this method for any other data which you have. Okay, we have done this in the past with even, the LCO, the Las Cumbres Observatory. They have robotic telescopes. And you can even use that to get images. Or if you have your own telescope with which you are getting images, you can use that to actually create this catalog. You can apply it to any of these, right? Okay. So once again, I'd like to acknowledge my thanks to Tim Hamilton because a lot of this stuff which is there has been done by him, right? So I'm kind of taking a lot of the stuff from him and thanks to him. Okay, so how are we going to get our data? We are going to get our data from this source called the SDSS, which is the Sloan Digital Sky Survey. Okay, so what this Sloan Digital Sky Survey was basically, like you can, I mean, like it's there in the name, it's basically a sky survey. So a long time back, there was the Palomar Observatory, which had made a whole sky survey, observing the whole sky, but that was observed on photographic plates. Now, these photographic plates were taken sometimes in the 40s or the 50s, but by 1980, 1990, the complete set of photographic plates was digitized, and that makes up what is called the DSS survey, which is the Digitized Sky Survey, right? That is the DSS survey, and that is the most commonly used survey if you go to any observatory or you're looking for any kind of data about the sky. You'll generally find the first default option which comes to you is the DSS option, okay, where you actually use the DSS data or the Digital Sky Survey. But you obviously remember that the Digital Sky Survey was taken on photographic plates. It was not digital data. It was digitized later on. The Sloan survey was actually an attempt of actually doing the sky survey from digital format from the very beginning. So what you can see is here's the telescope which was used for digital sky survey, and basically it surveyed the sky, and based on that got out many data releases. So you can see this is written the data release 13, but there are many, there was data release 1, 2, 3, 4, 5, etc. Each time they add on the old data or they improve better techniques to get the data in a better format, in a better form, and that's how you have different data releases available of the SDSS. So we are going to use the data which we get from SDSS. So now I'll request you to actually go along with me, and I'm going to, I hope you can see my browser, right? And I've kept this just in case. What you can just go is do sdss.org. Okay, this is a website you need to go to, which is the main website of the SDSS, sdss.org. Okay, so you'll click on this. I hope everybody is using their systems along with me. Please, let's move together. So this is the sdss.org, the website. And basically, what I'm trying to show you this is I want to show this to you so that you can see how you can actually get data on your own. You needn't limit yourself to the data which we do today. You will actually do it for all kinds of data of your own, right? So if we actually, you will see that there's a lot of stuff available on this website. You can see that there are even tutorials and different ways in which they actually show you how can you use the data, how can you explore the data, what are the various features about the data, and things like that, right? So you'll find a lot of extra stuff on the website. So you should start getting comfortable with using the website. Now you'll click on data because that's what we're interested in. So when you click on data, you'll see over here, there's data sets, imaging data, spectral data, etc. Because what was done is not just these telescopes, this is a basic Sloan telescopes which were used, but along with this, a lot of supplementary ground-based data was used, which actually added spectroscopic data. If you remember in yesterday's tutorial also, I showed you that by using radial velocity data, that is the step where you actually manage to get the mass of the planet. If you don't do radial velocity measurements, you will not get the mass of the planet. And similarly, in many observations, you always need to couple your photometric observations with spectroscopic so that you can get much more meaningful data. So now over here, click on imaging data, right? We are looking for images. So please click on imaging data. So you go to sdss.org, click on data, click on imaging data, right? Now, just for your convenience, there are 3 different ways in which you can actually access image data with Sloan. So one is what is called Sky Server, which is a very popular tool. It just depends upon what you find more convenient for you to use. There's another method called Cache Jobs. Cache Jobs actually uses what is called SQL, which is a query language. And the advantage in using Cache Jobs is that supposing you want to retrieve a very large amount of data, right? For example, you want 100 images or 1,000 images, then you can actually do it through Cache Jobs so that it will do it in an automated way. What we are going to do today is we are going to use the Science Archive server. In principle, like I said, you can use any of these servers depending on what you're, comfortable with. right? So please, I would request everybody that in case you have, you are left behind or you did not get into the thing, please tell me. So now click on Explore SAS Imaging. Right? And now we are going to look for the imaging data of a single globular cluster, which is NGC 5466. Okay. So this is just this is one of the globulars for which the data is there of Sloan, SDSS. So I will look for that. Yeah. And what we are going to do, there are many options. You can see there's a single field search, bulk field search, coverage check, depending on what kind of data. But since we want only a single globular cluster, we are going to click on single field search. So I will click on this, right? Now what I'm going to do is, if there are people who missed on this, I'm going to I'm copying this URL and I'm going to give it to you in the chat window. I'll give it to you in the chat. So if somebody missed on the thing, right, you can directly get onto this website, right? This is the same location where I'm sitting at just now. Okay. And now we are going to add in over here our cluster, which is NGC 5466. Okay. This is the cluster for which we want images. And you'll click on submit. So please type NGC 5466 and click on submit. People who've come in late, you can use the link I've given on the chat window, and you can use that to directly come to this page. Oh, yeah, we are already here. So here you can see this is the image of this globular cluster, right, which is sitting over here. And you have all these options. Sloan, they observed in 5 photometric bands. Okay, this is the U band, the G band, R band, I band, and the Z band. And you can even get a JPEG image. So what we are going to do today is we are going to download images of this globular cluster in 2 bands, the G band and the R band. So click on G band. Yeah, click on G band, and this is the image. So I hope you have a dedicated directory, right? Like I have one over here. You can see PP3 with Day2, right? So please download your, I downloaded it earlier. So my files are already over here and you can put it over here. Yeah, please organize the data so that you can find it easily. So that is your G band data. And then we also will download R band data. So click on R band and download it at the same location, right? So we are going to get basically 2 images. One is the image of G band and one is the R band image for this globular cluster, which is 5466. Okay. Now we need to download some other software. I had already sent you a mail about it, but I will just walk you through it. The first one which you need to this thing is something called DS9. Okay, put DS9 astronomy, otherwise you'll get all kinds of other hits. So put DS9. This is Deep Space 9. This is the software which is used to look at images, right? We've just downloaded 2 images. We want software with which we can look at those images. If you noticed, when we downloaded those images, they had an extension .fits.gz2, right? So this FITS format is the format for images in astronomy. We don't use JPEG and PNG. We use FITS because that lets you do some more operations on this thing. So get into this website for DS9 and there's download over here. Click on download. And depending on whatever system you are using, Linux, Mac, Windows, whatever system you're using, please accordingly download DS9. The good part about, even in Linux, whatever flavor you have, whether using Debian or Fedora, whatever, if you're using Ubuntu, you'll click on Ubuntu and you'll get this thing. What is good about, you basically get a file which you just have to double click. You don't have to do anything when you're installing these things. So most of these software are all Java based. So it doesn't make it a difference. It does not have a clash with your OS generally. Right. So first thing you all need to do is everybody needs to download DS9. If there's somebody who didn't manage that, please let me know. Yeah. So please download DS9. Right. The other thing I need you to download is a tool which is called APT, or you can call it Aperture Photometry. It is called the Aperture Photometry tool. So you can write APT tool or Aperture Photometry, right? You can Google this, and the first hit itself you'll get over here, which is Aperture Tool Photometry, right? So I hope everybody's got their DS9, right? Like I said, DS9 is the basic tool you need for visualization of astronomy images. The other software you need is Aperture Photometry tool. So you click on this, the APT tool. I've sent you this link in the emails also. And as you scroll down over here, you can see there's downloads on the top. So click on downloads. And like you saw in DS9, you have the downloads available for if you have a Windows machine or you have a Mac, right? There is one for Linux also. Where is the Linux one? There was a Linux one also. But actually the Linux one has a few issues. So if you have access to a Windows machine or a Mac, that is the best. You can put it on Linux. Where's the Linux one gone? I don't know where is the Linux one gone. Yeah. Okay, then I think he says you do this all machines. Except, okay. So for Linux, use the first one. Use the first one for Linux if it's not Windows. For Windows, use the second one. And for Macs, use the third. Okay. So people who have Linux machines, please use the first one. Windows, use the second one. Mac, use the third one. Right? And it's quite a straightforward procedure of you'll have to unzip your file in Windows. Even in tar.gz, you will have to unarchive your file. With DMG, you just have to double click it and that will install your software, right? So I will just pause a little bit to check in the chat whether has everybody managed to install these two softwares. And we will also need a TopCat, which we use that. Ajit, what is not downloading? Please write in the text, what is not downloading? The data or what? Urvashi, you have a problem, you can separately talk to me on WhatsApp or something, right? And I'll check your problem later. APT tool is not downloading. No, you double click on it, it should download. I hope you're on this page. You double click on this, right? You double click on this, it should download. Can someone resend the link to the data? You want the location of where the data is sitting, or Brandon? So I will, okay, wait, I hope you can see my screen. So the data has to be taken from here. Okay, here I'll show you this thing. Okay, I can give you this link. So what I'll do is for data, people who want the data, I'll give you the link and then you scroll over here and download from G band and R band. Okay, so I'll give you this link. Yeah, so people who have just joined, go on to this link. Brandon, you can go on to this link over here, which I've shared, and you can see it over here. This is the very same page. And here, click on G band. Click on that. This will give you the file for G band. And click on R band. This will give you the file for the R band data, right? So I hope people are managing that. Yeah. So Barenya Dave would like to know what are all these different bands. So essentially, you can see in this is the wavelength, which, these are different wavelength bands where the U band is closer to the ultraviolet. The G band is a green kind of thing, a green color. R is close to the red, so it's longer wavelength. I band is similar to the I band which we have in infrared, it's towards that side. And Z is also, actually Z band is I, cousin's I, closer to cousin's I. If you Google, you can actually get the wavelengths of this thing. So these are just different filters which are used to actually observe with SDSS. Yeah, so here you can see the ultraviolet band is 3543 angstroms. The green filter is 4770. Red is 6231. Near infrared is 7625. Right? So these are all the different wavelengths. Today, hopefully, if we get some time after we do this exercise, I will explain to you all a little bit about observations maybe. I first thought I'll do some theory, but then I was worried that there won't be enough of time to do all that stuff. So we'll do that. So I hope everybody now has the data and has APT tool running as well as DS9, right? If there are no questions, we'll go ahead, right? So first thing I'm going to do is I'm going to open DS9, right? Yeah. So please double click on DS9, right? Double click on it and you will open this window, right? I hope everybody has this. I can see some more messages. APT tool is not downloading. I'm sorry, I downloaded it earlier, so you just continue double clicking or whatever. Or I can try sharing if there is. Maybe we can look down online.
Ma'am, I think, hello ma'am.
Yeah.
Ma'am, I think to download APT tool in Linux system, we have to use terminal with wget command.
Okay, then it's working.
Then it will work.
Okay. So you can share that command on the chat window for people who are using Linux, right? I think for the Windows users, it's pretty simple. You download the zip file, unzip the file, double click it, and that will install it, right? So for Windows, just unzip the file, double click it, and it will install. For Mac, you just have to use the DMG file. You'll get a DMG file, you double click that, that will do it. And Linux, like someone mentioned, you'll untar the file because you'll get a tar.gz file. So you'll have to first unzip it and untar it, and then you can, there'll be an install file, I think. There's an install or a readme or something. So yeah, so thank you. Subhadeep Datta has shared the command you can write for installing this. If you're using a Linux machine, please use the wget command and download it. I hope the others have managed, right? So now what I'm doing is that since we downloaded DS9, I'm sure DS9, nobody had a problem. You can click on File and we will open the G band file, which we just downloaded. So you can see the G band is lightened up and I'm opening it and this is it. So now this is the tool used in astronomy to actually look at images. Now in astronomy for images, you can see there's a file name .fits, right? So this FITS is called the Flexible Image Transport System, which is a format specially made for astronomical images, right? Now you can see that on this image, you're not seeing anything much, right? And that's because of what is called the scaling, okay? You have to scale. So the best thing is click on scale, and then this is a linear scale. If you click on log, you will see suddenly you'll now see your image, right? So I hope people can see that, right? Another thing which you can do if you have a mouse is you can press on your right button. So what I'm doing is I'm pressing on the right button of the mouse and I'm adjusting the brightness, okay? So here you see the stars are black, I can make them white, I can change the contrast, I can adjust my image, right? This I can do with a mouse, if you have a mouse. Otherwise, you can try all these other options. This was the log which gives you the best one. You can even try power. Power gives you nothing. Square root is not too good. Squared is also bad. This is also bad. Histogram is a bit too much. You see too many things. And that's why the best option for most of you, if you look at your image, you will see that you can see the best image if you actually scale it with this thing. The other option you have over here is zoom, right? So you can zoom in if you want, and you can zoom out if you want. You can zoom fit if you want, right? The other option which you have in DS9 is color. I can color my image. This is a gray image. I can make it on heat, which is a yellow kind, or on cool, which is blue, or rainbow with more colored images. And I can adjust the contrast of my image so that I can look at the image better, right? So often in astronomy, what we need to do is we need to adjust the contrast so that you can see. Supposing I'm trying to look at this particular star, which is quite a faint star, I may accordingly want to adjust my colors as well as my background, etc., so that I can see the star better, right? So I may put it on gray, or I may put it on heat, or whichever option I want, and accordingly adjust it, right? So this is a skill by itself which you will get when you learn how to use this window. But essentially, what you are doing is you are enhancing the image. You can also do various things like you can mark out regions in your image, right? So if you mark it out, you can mark out a region, right? I can pick up a certain region of this image, right, which I want to look at. I can even do various things like I can, I can make a crosshair, I can make color bars, I can pan, I can zoom, I can do various things, right? So these are all options which are there with this. I can also, if I want, I can also add contours to my image, right? And these are contours to the image where I can even adjust the contour parameters. So if you click on contour parameters, you will see that I can change this thing. I can change the number of levels. I can generate it and apply it. It didn't make much of a difference to this image, but in principle, you can do various things, right? And now if I want to look at my other image, this is my G-band image with contours. So I'm going to remove it because it's a little messy. And now if I want to, for example, look at my R-band image, there is a button called frame. I can say new frame, right? And in my new frame, I can open and put my G-band image. This is my R-band image. So here is my R-band image. And if I want to see both, you will say frame and you will say tile frames. So here I have my R image, and this one is my G image. So I will make this another color. I'll make this blue and I'll make this red. So this one is the G band image. You can see this written on top over here, while this one is the R band image, right? So I can actually look at both these. If I want, I can also blink these images. By blink, I mean one above the other, right? And why am I blinking these? Because you can see that there's a slight shift in both the images, right? You see my, if my cursor is on this star, you can see the position changing, right? So I hope you can notice how there's a slight shift in the G band image and the R band image. This we need to keep in mind because when we are doing the photometry, when we are creating catalogs, we need to remember that the same pixel position does not apply to the same star in both the filters, right? And therefore, what we are going to do now very soon, I will make it back to single frame. What we are going to do is, like you noticed, both the images have a slight shift in them, and therefore, we will instead use these coordinates. So I will, you see, WCS is the World Coordinate System. So if I say I put it in degrees, then you can see over here, this is in degrees. Okay. So here you can see that, you see when I'm looking at this star, for example, right? This star has these coordinates, right? You can look at the coordinates on top, alpha and delta, 211 and 28.45, right? So similarly, even for the other image, which is the, I can say the next frame, for this image, the same star is this, right? And you can see, I can change the WCS coordinates to degrees. And here you can see, here your thing is in degrees. And there's a slight shift, but you can see that these images already have the world coordinate system on the image, right? And therefore, what I'm going to do is to identify the same star in two different filters. I am going to use the WCS coordinates, that is the right ascension and the declination, so that I can match them to actually identify the same star, right? Otherwise, the problem is both these stars, right? This star is slightly shifted in both the filters, right? So I cannot use pixel coordinates. So this image has two kinds of coordinates. One coordinate is the coordinate which I have, which is the array deck, right? And the other coordinate you can see is 392.1169. That is the pixel coordinate, right? The digital image has certain pixel positions, and these are the pixel coordinates. But like I showed you, since both the images are shifted, slightly shifted, we are going to use the WCS coordinates or alpha delta to identify the same star in two different filters, right? Because they are slightly shifted. Yeah. So Purvika is asking, why do stars coordinate get shifted when we see through different filters? Okay, because generally what happens is that when you observe with a certain filter, and then you're still looking at the same object, but telescopes are very delicate instruments. So what happens is, with a very small impact, the position of the telescope can slightly shift. You see this shift which is there in these images, a very small shift. It's a very small shift, but it is observable for us. So what happens is, in principle, if you want them to be perfectly aligned, there is something called an auto guider. So if your telescope has an auto guider, you can ensure that they will all be at the same position. But in this case, they were approximately same position, but slightly shifted. So when you have images in different filters, you should always check whether they are, sitting one on each other. Are they perfectly aligned or not? Today, what I'm showing you with array deck, in principle, if you want to continue with pixels, supposing you're using this on your own home telescope, right? And they are on pixels. So there's no problem. You can actually shift your image so that it falls on the pixel you want, right? So even that is very much possible. So I think it would be a good idea. I'm slightly changing my thing, but I think I'll show you a little bit about astronomy images, and just a minute. So I'll stop the share. Yeah. And just a minute, I'll just show you, since the topic came up, I'll just show you a small thing. Right. So astronomical images, these are digital images. Okay. And digital images, they basically are like a grid, XY grid, right? So, yeah. I hope you can see the screen, right, which has a image. So in astronomy, what happens is the images are like a 2D grid, right, XY grid, and each position has some pixel value, okay, some brightness. But this is essentially a black and white image, because what we basically do in astronomy is that we use what are called CCDs. These are charged coupled devices, okay. So charged coupled devices exactly is what you have on your digital camera, on your phone or in your laptop, whatever. You have these kind of digital cameras, right? And what this basically does is this 2D grid which you have, which is your digital image, right? It basically collects photons. So here are the photons which are falling on this grid, and it counts how many photons. But since it does not know, we add in what are called filters. Filters will only permit photons of a certain wavelength or frequency. So what happens is, on the digital image, like this is how you actually take photographs, colored photographs. When you take colored photographs, at the same time, different pixels, some of them are meant for green light. So 50% of the pixels all are for green light, which is the in-between color, 4,500, 5,000 angstroms. Some of the pixels are blue pixels, which are for bluer light, which is shorter wavelengths, say 3,000 angstroms. And then some of them are the red ones, which will take in wavelengths more than 6,000, 7,000 angstroms. So what happens is, when light falls on this thing, on this digital camera, depending on the wavelength of the light which comes in, that filter will permit the photon, and accordingly there'll be a reading. And this is exactly how we take colored images on digital cameras, on camcorders, scanners, etc., your phones, etc. And what happens is, with that you will actually get an image. In astronomy images, what we do is we add filters. The filters are added one by one. So you first take the blue filter, then you take the the green filter, then the red filter. Like in Sloan Digital Sky Survey, you have to use 5 filters one after the other, right? And when we use these 5 filters, we actually add them up together to create what is called a RGB, or a colored image, right? So astronomy colored images are made by adding on images of different filters. And like I've spoken to you, these images are basically in a format which is called the FITS format, which is the Flexible Image Transport System. Okay, so what you basically have is you have X, Y, you know the size of the image, okay, and you have a count for each position of a pixel. And the FITS file also has what is called a header. Header has important information about the image, and it has some more metadata, right? So that's a FITS image. So now in astronomy, we actually think of images like a matrix. So here you have an image, right? And for each pixel position, you have a certain count, right? And when you add this all together, the certain counts which you have, you get an image. So the image is something like this. It's an XY grid with a certain value of counts at every point, right? And that is what we use to actually, so depending on, supposing like you looked at that image, you had that image showing like this, but you saw that when we changed the scale, we changed it to log scale, you could see the image better, right? So if you just get in the image, it could be like this in linear scale. If we convert it to, you see the left one is linear scaling. In this way, if you convert it to log, or you put cutoffs. So by have digital images, we basically have the advantage of doing arithmetic operation on images. We can add images, we can subtract images, we can divide images, we can do various things. Now in this image, what you can see is this is what is called a composite image. It's basically a combination of 2 images. I'll show you which 2 images. This is NGC 281. So this is the image of this thing. This is called the Pac-Man Nebula in optical. So you can see in optical light, there's a lot of gas and dust, and therefore you cannot see many stars in this region. The same thing here, this is a Spitzer image, okay, which is an infrared telescope. So here you can see all the gas and dust sitting on this location in this region. And then if you go ahead, here you can see this is again an infrared image. And here you can see this is the X-ray image. If you use the Chandra telescope and look at this object, this is the image you get in X-ray. So the image which I showed you, this image, is actually a combination of all these images. The purple part is the X-ray part. Then you have the infrared part, which is coming from Spitzer. This is another Spitzer image, which is the warm. There are 2 components of the Spitzer image, and this is the optical image. So you can add all these together to get a composite image like this. So this one basically has Spitzer with X-ray. So what we do is we combine astronomical images like this so that we can study different sources and see their properties, right? So, and that gives us the advantage of doing what is called image processing. That means we can process the images, right? So I'm going to exit this and we'll go back to our thing and we'll go back to DS9. So I forgot to show you that in DS9, if you click on file, there's also display header. Click on header and you see here I have all the important information about this image. Sorry, I'm not sharing the screen. Okay, one sec. I'm sorry. So I'll share the screen. I hope you can see. Now you can see. Okay, perfect. So I'm sorry, but let me show it to you again. This is the image we were looking at. If you click on file and click on display header, right, you will see the header. So if you remember, I told you that astronomical images are FITS images, which have that digital image, which is the counts, XY counts, plus it has this header. A header has information about the image. So it's telling you the RA deck of the image. For example, it's telling you what is the, what is the object you are looking at, right? It's telling you what is, various other details. What are the other details? What is the date of observation? This is SDSS data. What is the, the azimuth altitude of the object, various things. So the header has very important information about the image, and therefore it is kind of packaged with the image, so that when you get the image, you get the header, and immediately you can check out from the header as to where is this image from, right? I see this image, immediately I can check the header. I can see from the header that this is this is an SDSS image of a certain object, which is at a certain location. It also tells you the exposure time. You can see it's 53.9 seconds. 54 seconds is the timing for SDSS images. So it tells you the exposure time. It tells you all these different parameters for the image, right? And that's what you're getting from the SDSS image. So I will stop with SDSS, and now we will move on to APT tool. I hope everybody managed to download the APT tool. If you did not manage to download it, I will try to get hold of those GZ files or the other files. Maybe if people have a problem, I can try this command and get it for the other ones. But I hope people have managed, right? So I'm going to open the APT tool now. What are we going to do with the APT tool? So I hope everybody managed to open the APT tool. It should look something like this. Have people managed? I'll open it again so that you get to see it. You can see my whole desktop, no? Okay. So I'm going to open APT. If you notice, this is a jar file, okay? It's a jar file because this is a Java file. So you just have to double click it, it will open. Or in Linux, you'll have to say Java -jar and say apt.jar, right? So Linux people will say, I'll put it down over here. You'll say Java -jar, exactly like you did it for Topcat yesterday, okay? So for jar files, if you want to open it, you have to say, give the command of Java -jar. And this, right? I hope everybody is with me. Should I check on the chat? Is anybody having a problem? Please tell me. I hope everybody is doing fine. Okay. Fine. So I'm opening my APT tool. Okay. Here's my APT tool. Now I will click on File, and I'm going to open the first image, which is the G-band image. So I'll say Open Image, right? And I'll come to this. So I'm scrolling down to the location where I have my G-band image, which is in a folder called WIA, and it's called TP3, and today is day 2. So I'll go to day 2 and I'll take G. So this is G. And you'll see that in this window on the right, you have the file is loading, right? So the G-band image is loading on that. Oh, I forgot to tell you that before you, I hope everybody's managing to open it. You may require to You may require to unzip those images also. I hope people manage to do that. I'll just help you. So in the folder where you downloaded the images, right? In the folder where you downloaded the images, you would actually have got these images like this, okay, with .bz2. Please, either you will unzip it if you're using Windows, right? Or if you're using Linux, you will also say unarchive. And if you're using a Mac, just double click it and it will give you the FITS file. So if I double click this thing, I will get this upper file, which is the unzipped file from this, right? So sorry, I did not mention this, but you need to unzip the image files. So this is the G-band image, this is the R-band image. I just double click it, and if you double click it, you actually get the other file. I'm deleting this because it's created 2 files for me. But otherwise, this is what you're going to get, right? And now this is the very image you are going to open with your APT tool. So when you open APT tool, open the G-band image of this, which is over here. I hope everybody's managed to do that, right? Here is the image. You can see this is the globular cluster, which is over here, right?
Can you do it on mobile, please?
No, this won't happen on mobile. I'm sorry. This will not happen on mobile.
Okay, thank you.
Sorry. Even DS9, I think, does not happen on mobile. I've never opened it on mobile. It won't work. Sorry. So you can have this over here, right? Now I'm going to show you how do we actually do photometry for this image. What do we mean by photometry? We want to count the number of photons. So you have these various objects in this image, right? And for each object, you are going to measure the light coming from it, right? So I'm going to again, I need to go back to my earlier PowerPoint. And yeah, so what are we doing? You can see my PowerPoint, right? Yeah. So what we are going to do now is photometry. What is photometry? It is measure of the light, right? Measure of light. So we'll measure the light, we'll detect sources, right? You can see that there are a whole bunch of stars in that field, and we will identify, measure, and create a catalog. Okay, that's what we are going to do in this exercise today. We are going to create a catalog of the stars which are there in that globular cluster. Now, how do we do stellar photometry? Supposing you have a star over here, right? The simplest way is what is called aperture photometry. Aperture photometry means you make a circle where you collect all the light coming from that star, right? And count the number of photons which are coming in that region. But you all know from normal experience that the sky also has some brightness, right? The sky also has some amount of light falling on it, which is, all over the place. And therefore, that light is also going to come in this circle. And therefore, we have to estimate not only the number of photons in the source, which is in this central circle, but we also have to estimate the number of photons in this background, which is, we define the background as a ring around the star, which has an inner annulus and an outer annulus. So this region around the star is what we are using to sample or to measure the brightness of the sky. So then I say that my source, the star, is actually source minus the background. So if I want to do correct photometry for my star, I need to measure the source and I need to measure the background, right? And that's what you do with what is called aperture photometry, which is what we are going to do today, aperture photometry. A better form of photometry is what is called Psf photometry. So what happens is that actually in reality, for every star that you are observing, you are actually going to get a diffraction pattern, right? You do not see the star as a point source. You see the star as a spread out this thing, which is basically the diffraction pattern. And this diffraction pattern is called the point spread function, or the Psf. So every star, instead of seeing it as a dot, as a spot, you see it as a larger, region, which is formed because of this Psf, right? Because of the profile, because of this star. So now what we basically do is, now every star is now not in that aperture, but it is part of this Psf. And therefore what we do is, for every star which we have, we actually scale it. We scale the star to the brightness of the Psf and count all the photons which have come within that thing to measure the brightness of that star, right? So like I mentioned, there are two methods. One is aperture photometry. You drew a circle, you collect the amount of photons inside that circle. And the second one is, you do a point spread function. That means for every star you have a profile. Within that profile, you measure the amount of counts, and then you count that, and that will give you the amount of brightness. So the difference between the two, I think I already mentioned it to you. Oops, sorry, I'm sorry. I mentioned it over here, that basically if you were to see what is the difference between Psf versus aperture photometry, what you are seeing is that what you're actually seeing is that the Psf is a more accurate way of measuring your photometry, right? While your aperture, you see that these photons are lost, right? These photons of the light are lost. You are only measuring within a certain aperture and you're getting this, but you're not getting these parts. But in the what do you say, in the profile one, you're getting everything, right? And so that is the difference which you have if you are actually measuring with a Psf or aperture. But today we'll do aperture photometry, and let's go back to our APT tool. So how do we do it? Okay, I've even listed the steps in my PDF, in my PPT, so I'll share that with you all. The first thing you have to do is you will click on more settings. I think I should, this thing is creating a problem. I don't like this. Okay. So your first thing you're going to click is more settings. Now more settings is going to tell you how are you going to set your aperture photometry. First thing is you can see that there's no aperture radial profile interpolation. We are not, interpolation means if you do not have data for a certain point, you are asking the data to interpolate. We say no, we don't want it to interpolate any data, just take the data as it is. The second important thing is the sky algorithm. The sky algorithm, like I told you, is we want to measure the background. How do we measure the background? One method is this model B. That means you make a sky annulus, and you make an annulus around every star and take the average value of that and use that to get the background. But in this case, look over here. If you see the star, you can see that around this star, if I were to make an annulus, there could be another star which can come in the annulus, right? So my sky reading will get wrong. And therefore, instead, I opt for model F. In model F, what happens is you take a sky background by looking at the region around the star, but you actually you actually look for the mode, in the sense if around this area, if I have a star, the mode will be high, I reject it. I only look for the region which does not have stars, right? So the model F is the best way to go if you have a crowded field. So a globular cluster is called a crowded field where you have lots of stars together, and hence you need to do this kind of a thing. You scroll down, and for SDSS images, we have to add what is called the 0 point. The 0 point is 22.5. Okay, so please note 22.5 is what you're going to do if you need to this thing. If you for the 0 point for Sloan Digital Sky Survey. Depending on if you were using another telescope, you may accordingly change the value which you have for your 0 point. Okay, so that will come over here. And now you'll say apply settings. Now that you're applying settings, it knows that you want model F. That means you want a non-sky annulus mode and therefore recompute. So you say yes. Okay, say yes. And it is now computing the sky background, okay, around every star, okay, by looking at the mode. It looks at the mode around the star so that it can get that. So you'll press on compute, and it's reasonably fast, it computes it. And you'll say close window, okay? So we have computed the sky for each of these, and I'll close this window. The next step you're going to do is we are going to set our sizes of our apertures. So you're going to click on this. But you see over here, click on big button on right to change aperture. So you are going to, now we are looking at this star, for example. So you can look at the way the stars are located. You have to go in for model F. Otherwise, you see that there's so many stars so close to it, right? So I will click on this big button. And here you can see, this is the aperture, this is the inner annulus, and this is the outer annulus. So obviously you can clearly see that this aperture is too small, right? The star is much larger. So I'm going to increase this from 5, I will make it 10. So the yellow circle, you see, has become 10. The inner annulus, actually we are not using it, but just for your this thing, I can make the inner annulus 15, and I can make the outer annulus, for example, 25. Okay, so I'll say this. So here you can see is this, right? So I will say, okay, I'm supposed to do this, but you don't need this because we are not using annulus, right? So there must be, before adjusting the sky annulus. Okay. So I will do this. So here I want to increase this thing. I will make this one more. So my major radius is this. This app tool also allows you to keep an elliptical aperture. So supposing I did not want a circular aperture, I could have made it, this is non-circular, I could have made it like this, for example, right? So you see, I can make an elliptical aperture. So you can use this if, for example, you were measuring the brightness, say, of a galaxy, which is elliptical. You can make your aperture elliptical. So you have only two options, either to make it circular or to make it elliptical. So I'm going to make a circular aperture and stop with this, right? So here's my circular aperture, which you can see over here, right? And these are my other two apertures. So I will say apply. Okay, I've applied it. The red one is the star aperture, green is the inner annulus, and yellow is the outer annulus. So I have applied this and I've got this over here. Okay, so I'll apply and I'll close. Okay, now what happens is I want to now make a source list. How do I make a source list? This is using list results. So first thing, you click on list results. If you have done some work before this, you'll see your list results file. You see I have things in my list results file. So I have to clear it. The first thing you have to do is clear your results file, because what this tool does is it will just add up other stars. So you say clear results and I clear it. I don't want it. And now I click on source list. So I make a source list by clicking on this. And I say create a source list. So what it's going to do is it's going to look at these. And I can even do checkbox to overlay sources. So I'll make this checkbox. So now you see when I say create source list, you can take all these default values. So don't worry. The source list, you can make a name of whatever you want, right? So I'm again going to go to my location in my system, which is over here. And this is my WIA, and my folder is called TP3. Right?
Hello, can you hear me? Hello. Hello.
Yes, we can hear you.
Can you hear me? So we'll be back in 2 minutes. There is an internet issue, so we'll be back in 2 minutes.
You need to let me in. You are there?
Yeah.
You are fine?
Yes, ma'am.
Okay. Okay. Okay, I'm sorry. I'm sorry, there seems to have been some net problem. I'm sorry. Okay. So I'll go back to where I was, right? So what you see is I said do a source list. Share screen. Oh, okay, okay. Thank you. So I'll share my screen. And if you remember, I'll just slightly repeat what I was doing. If you remember, we first did more settings, then we set the aperture, and then now I'm going to click on source list. That's what I did. So I had set source list, right? And I said create source list, right? And here I created source list. This is my create source list. And if you remember, we clicked on this reset source list file name, and I made this source list. I called it gnew, right? Or I'll call it, let me call it gn. Okay. Okay. So this is gn. Okay. So I say create source list. And after that, what you have to do is you will do automatically process source list. So press this. Yeah. Click on automatically process source list. And this is just going to create your source list. Okay. This is not yet doing photometry. This is creating, so this list which we've created, it creates the list of the sources, right? But now what we are doing is it will do the photometry. Very simple. So click on this, you see that it has detected 2,388 sources, which are marked over here. So please look at your image and see whether it's correctly identified stars, right? So you see that there are circles around all the stars it has identified. Now you can see that there are some fainter sources which are not identified. So that's because of the settings we have put that it has not taken certain fainter sources. You have to do further adjustments to your settings so that you can detect fainter sources. But at present, it has detected only these sources, right? So these are the sources which it has detected. This may take a little long on different systems. Mine itself is taking a little long, but it's okay. Right? So now it's made this source list. Now what do I do is I open list results. I look at list results and here's my source list. So this is my photometry file, right? So we remember we had 2,388 sources. So you can look over here. We have 2,388 sources, which we were told earlier, right? These are my 2,388 sources. Now I want to save this photometric data, and you can see that this is the RA deck, etc. So I'm going to say export contents. I'll export the contents. You'll have to reset CSV file. Click on this, and here we'll say my ng fort, right? So ng fort is this file .csv. If you remember, did I say that yesterday? No, I didn't. CSV is a comma separated file, right? So if you have a data file, there are different formats in which they are saved. This one saves it in CSV format, which gives you a comma after every value. Okay, I'll show you what the file looks like, but we'll put this file, we say choose, and I say create CSV file. Okay, so if I can even show you what this file looks like. See, this is our file. This is the one we just created. If I were to open it in a text thing, you will see it looks like this. You see, after every value, there is a comma, right? After every value, there's a comma. This is a comma, this is a comma. So I can control F, comma, right? So you can see all these are commas. After every value, it has basically put in a comma, right? And that is how it basically, well, what is a CSV file, right? A better way to look at a CSV file is by using Topcat. Okay, so let's open Topcat. I hope you are all with me. Open Topcat, click on it and click on file and say load table, file browser. And here we look at our ng fort CSV. Okay, the table format, here you have a drop down menu. Please select CSV. Okay, select CSV and say OK. And now if you look at your data, it's here. You see it's in the form of these many columns. You have many columns. What are these columns? You can see this is the position of the star, the RA, the deck, right? And then if you move ahead, you can see this is the brightness of the star, which is giving you the magnitudes, right? 19th magnitude, 17th, 16th, whatever. This is the error in magnitude uncertainty. And this is giving you the sky value, etc. Right? So this is what we call a photometry file, where we have photometry for all these objects which are there over here, right? So we already have a catalog for this file, right? In principle, you can even load this catalog in DS9 also and look at it. It will tell you for every star. Now what we need to do is we need to create a similar catalog with R band, right? Remember we had that image in R band also. We need to open that. So now you'll say apt file and you'll say open image. Now here, since you already had an image over here, it's giving you these options, right? Read in the new image and clear all images or whatever. So you click on A, read a new image. And the new image you're going to take is the R band image, right? If you remember, we downloaded two images. One was the G band image and one was the R band image, right? And you will click on this R band thing and say open. And now APT tool has opened the R band image, right? So what you are seeing over here is the R band image here. Here you can scroll and see. This is our cluster. This is the cluster in R band, right? We looked at it already in G band. Now we want to make a similar table for it in R band. So the first thing, again, you'll go through the same steps which we did in the previous case. What do? First, you say more settings. More settings, you click on model F, and here for 0 point, you take 22.5, right? 22.5, and you'll say apply settings. You have to say apply settings because again, it has to estimate the sky for R band. So you'll say apply settings. So you say want to recompute, you say yes. So I recompute and I'll press on compute. So now it's computed the sky in R band. I'll say close window. And this is all apply settings. Oh no, we already did it, so we are not going to do it again. I'll say close window. The other thing we have to do is now to set up the aperture, right? We have this thing, we want to set the aperture. So I'll click on this big button here, and here is my star. Right, here's my star. Here is my big button, and here's the star, right? And here we'll go ahead with the same settings which we had for G band because they are similar. You can see that it's not very different from what we had in that band. Right, so we can take this, and let's take a better looking star around a better one. Right. Okay. And here we put this and we can look at this. So let's go ahead with the same aperture which we did in the case of G band because R band and G band don't vary much. So I can just say apply and I'll say apply and close. Right. So my aperture is also set. Yeah. Now I will check my list results. If you remember, this list results has the table for G band. I don't want it to add on to the R band over here, and hence I'll say clear contents. So you say clear contents. Are you sure? Yes, I want to clear it. So I'll clear the contents. Okay. Now the thing is, I want to make a source list, but I want to make the source list using the array dex which I had in the G band image, right? So how will I do that? We'll go back to TopCat, right? And if you remember, we have my ng fort. This is my ng fort over here, right? Which is the photometry with the G band. Now what you're going to do is for TopCat, right? Click on views, click on column info, right? And here what we want to do is we want to only retain array deck. So I'm going to click on column. I'll say hide all columns and I will click on only array and deck, right? I only want it to display array and deck. So what you see over here is now this thing is only displaying this. The other data is there, but it is not displaying it. Okay, it is only displaying this data, which is the array deck data. And now I want to save this file. So I will say file and I will say save in ASCII format. I will say ng, I can say ng coordinates, right? Because these are the array decks for them. So I'll say nj quads, okay? And I save it. Now I'll go back to my APT tool and I want to now make the source list, but I want to use that data, right? And therefore I will click on source list. But now if you remember previously we did create source list, but now I'm going to say choose source list because we already have a source list which we have with array deck. So I will do choose source list and I will now take up the new one which I took, which is ng quads, right? And now most of you all will see this, we will get an error message. It does not like this file. And therefore what we are going to do is I'm going to go through this. I'm going to go to ng quads and I'm just going to, if you remove this hash mark, right, you will see that it works. So either you remove the hash mark or if you want, you remove this whole line. There are two options. You can even remove this whole line. That will also save it. Or you remove the hash mark. So I come back over here I say choose source list. Now I say quads. Now you say it'll accept it, right? I have to also change this to equatorial coordinates because otherwise the system is going to think that I'm looking at pixel coordinates. But now I'm already looking at equatorial coordinates, right? Because I am using the equatorial coordinates of the G-band filter to match it to the R-band filter so that I do the R-band photometry for those same stars using this, right? And I can now press on automatically process because we have a large number of sources, we'll do automatically. If you have only one source, we can even do manually, but we'll do automatically. So click on automatically and you see that now here on my image, you'll see these sources which are detected will get overlaid. The green thing will come on them. Green circles will come at the points at which we had sources, right? So here you will see it's processing it. We have set checkbox to overlay sources on image and it should do that. This is the one step which takes a little long. It is also possible that your system may hang. My system is not hanging, but your system can hang. If your system hangs, you'll have to close it and open APT tool once again and again run it, right? So sometimes you may have such a problem. Depends upon your system and how does it take it. Yours is running fine? It's fine. Okay, very good. But some cases it can hang or it can stop. The only solution to that problem is that you reopen it, restart it, and do it once again. Okay. So we'll have to do it like that. Yeah, so we are almost getting done with this, and you can see it's done it. Okay. Why did it not mark it? I'm wondering. So I will now click on list results, and you can see here are my results, right? And you can see again it's got these things. Again, how many sources? I closed that box, but you see that this is detected the same 2388 sources, right? Exactly like that. You can see here I have my RA deck, right? You can see this is the magnitude of the source. This is the uncertainty, the error in magnitude. So that's essentially what we want. We want the RA, the deck, the magnitude, and the uncertainty. So now I'll say export contents, reset CSV file. And now my this thing is, instead of gfort, I'm going to call it rfort, right? So my first one was n_gfort.csv. Now it is rfort.csv. So I'll say choose and I'll say create CSV file, right? Now my APT tool work is done. I go on to TopCat. If you remember, we already opened our gfort CSV. So let's go back to views and we go back to column info and we tell it to actually show all columns, right? Reveal all columns, right? We had hidden the other columns because we wanted to get the RA deck list, but now we will say show all columns. So we say show all columns, right? And then I say file load table. And now I'm going to load the R-band photometry file. So I will do this and I will do this nrfort.csv, which is this. So you can see this, right? I can show you just a simple thing that, for example, if I were to plot it, right? If I were to plot first, let me plot the G-band. If I were to plot G-band, RA versus deck, it's something like this. On the same area, I can plot R-band. RA versus deck. You see these are almost coming one on each other. So I will slightly change the form. I will make this a square of a slightly bigger size. Right? So in this, if you see, actually it's exactly reversed. This one has come to be the R-band, this should have been red, right? And this G1, I should have made it green. Yeah. So the G-band stars, if you look in this image, they are the green dots. and the R band stars are the red squares, right? So you can see that we have exactly overlaid these two catalogs. We have a catalog of G band data and we have a catalog of R band data, and we are exactly putting one on top of the other so that we can look at both these sources. So we have one catalog which is for G and one is for R. Now TopCat very comfortably lets you match two catalogs. So if you look at the matchstick over here, there's a matchstick over here. Somebody's asking me something on chat. I'll just pause for a minute and you can let me know if there are questions. I'll stop this share, and in case APT tool not running, I have downloaded. Okay, yeah, so APT tool, there are some problems with APT tool, but you can try it out later and we can sort it out separately. Ishan is asking about the hash workaround again. So if you remember, I showed you this file, right? This was the file. 1 minute. Yeah. So if you remember, there was the file which had coordinates, right, Ishan? So there was a file which had coordinates, right? And this was ng coords. The first line had the header information, in the sense it had the name of the title. So the name of the title was RA and DEC, right? And somehow APT tool does not like that line which has that thing. So all I wanted you to do for the hash workaround, oh sorry. Okay, so yeah, so sorry, Ishan, you can see this thing ng coords, and ng coords is this file which had the RAs and DECs of the sources, right? Now the problem was that TopCat creates this file. When it created the first line which had this. It had this, okay, which had aperture array, aperture DEC with a hash. Okay, this is the standard way in which TopCat saves your file. But the problem is APT tool does not like it if you make your file like this. It does not like this. And therefore, when you want to provide this file to APT tool, you need to delete this line, right? And you need to take this one step up. So that is the only thing you have to do with the hash thing, that you need to remove that hash line because APT tool does not like it. Okay, that's the problem with that. Yeah, I don't see any other questions. So I'll go back to TopCat. Yeah. If anybody has any more questions, please let me know. But otherwise, we'll go back to TopCat. So now what happens is, we now have, like I showed you in that plot, right? If you remember, I showed you a plot which showed the overlaying of the G band and the R band stars. They are both sitting together. Now what we want to do is we want to make a single catalog which will have both these things. Okay, so use this matchstick, double matchstick over here. This basically matches two catalogs. So the first catalog, you say it's with sky, means the coordinates. I want the maximum error to be 1 arc minute, not more. Actually, it can be lesser also. And here we are going to take our first file, which will be our GFOT CSV. The RA column will be, you selected aperture RA. The DEC column is aperture DEC. The second file is the catalog for R band. First file is catalog for G band. Second file is catalog for R band. RA column is given over here, aperture RA. DEC column is given over here, aperture DEC. And what we do is we match these two. So you say go. You press on go, and here you can see 2379 pairs found. Right? It did not match all the 2388 because we know that the two catalogs are slightly shifted, right? And there can be a slight difference between the detection. You can even plot the result like this. You see this plot result here. I'll show it to you. You can look at this, and you can actually, I can zoom this and oh, it was supposed to be doing that for me. Where did it do? Link. It's supposed to be showing the link. Can we not see the link? Ah, okay, okay. The link is very close. So what you see is it's showing the distance between the red and the blue stars, right? So let me go into one part over here. I'm zooming in, and you can see that This is the position of one of the stars, the green, and one is the red, right? So you can see that this is showing you the shift, right? There's a slight shift between both. We know that there's a shift between both the catalogs, right? If you remember when I blinked both the things, you saw that there was a shift. So I have actually, you can see that they don't exactly sit one on another, slightly shifted, right? So that is shown over here. But now we have a matched catalog, right? And now with our matched catalog, you can see that this is match 21-22, means it has matched these two catalogs. You look at the file. This is how you see RA1, RA, so the 1 all refers to the G band and the 2 all refers to the R band, right? So this is image 2. This has all the details about image 2, and this one has all the details about image 1. This has all the details about image 1, right? So RA1, etc. This is all to do with image 1. And then when you move over here, you can see RA2. This is all dealing with image 2, right? So now we have this and this, right? And I can just show you in advance what are we going to do tomorrow with this is we will use this file to create what are called color magnitude diagrams, right? And for that we need the G band and the R band, okay? Which I will talk to you about it tomorrow. What is the HR diagram, right? So the color magnitude diagram. I won't show that to you today. Oh, I can even show that to you if you wish. So I can actually plot it. So if you see the plot over here, I can plot. See, this is the G band. So the G band over here is magnitude 1, right? And R band in the same file is magnitude 2, okay? And on the y-axis, I can plot magnitude 1, and this is the kind of plot you will get, okay? This is called a color magnitude diagram. We'll talk about this more in detail tomorrow, okay? So for a color magnitude diagram, you need a magnitude, brightness in one band, and you need a color. By color, you need difference in magnitudes in two bands. But we'll talk about this tomorrow, okay? So for today, what I want you to do is I want you to try to get this combined data set, because this is what we are going to use tomorrow, right? We are going to use this matched data set tomorrow. In case you have a problem in this thing, tomorrow I will share the CSV file so that you can continue working with me using the CSV file, which will be with TopCat only. So tomorrow we won't be using any APT tool. I agree that there are issues with APT tool. So in case you've had a problem that your APT tool did not work and you could not create the catalog file, for tomorrow's exercises, I will give you this matched file so that you can do the exercises for tomorrow, right? But APT tool works very well on Windows machines and on Macs. There can be problems on Linux, but not always. Sometimes it works fine on Linux also. It just depends upon your system and other parameters. Okay, so we'll stop with that. But I want to tell you one more thing. This is what I showed you is if you were using SDSS data, right? If you were using SDSS data, then this actually showed you how do you actually, how do you use SDSS data. But there are images, many more sources from which you can get images, right? What are the other sources? So for example, yesterday, if you remember, we did the MUST database, right? Which is must.stsci.edu. This is where we got Kepler data from, right? So from this very website, you can get more imaging data. So for example, if you're not working with SDSS data, you can work, for example, with HST data, right? So basically your purpose is you want to get an image, right? And you know, HST data is Hubble Space Telescope data. That's best quality data, very good quality data. And supposing you want to look at Hubble Space Telescope data, right? You can actually use this MUST page to do that. So for example, over here, I'm now going to look at another globular cluster, which is called M75, right? So on the MUST page, very simply, you just say M75, right? This is M75. And then you say search. So you say search. And this is M75, which is a globular cluster. Right. Okay. And I'm actually using my mouse. I can zoom in and I can zoom out. Right. Now what you see over here is, sorry. If you look over here, like I said, I can zoom in and zoom out, look at the images. And you can see that there's various squares, very strange looking squares and stuff like that. These are what are called footprints. That means these are the images which are there from different telescopes. Okay. So you can see they are all listed over here. There are a whole bunch of images from different telescopes, right, which are shown over here. Now, let's say for our example, we decide we want to use HST data. So I can just click on HST. Saying I only want to look at HST data, so Galaxies, IAU, these are all different telescopes, and it's showing me data from these different telescopes, right? Now, let's say I only want HST data, right? And then I want to specify which instruments I want, right? So this is the WIFPIC 2, which is the first camera which was there on HST. This is the ACS camera. There's also this other camera, which is the WIF-C3, which is in UV. So let us say we want to see this data, okay? I say I want to see this data. And this is it. So I say I want this. I don't want HAP data. I only want HST. So I don't want HAP data. I don't know why it's giving me HAP data. I only want HST. No, I don't want HAP. I don't want HAP. Okay. And here we have selected this thing over here, right? Now you look over here on the right hand side, we have various images which are there over here. So you can see that these are images of the same cluster, right? And you can see that this is giving you the details about the images. So we are going to basically deal with these images. Where is the images option? I only want images. I don't want anything else. And therefore over here, these are the two images which I have, right? And if you see over here, these images are HST, Hubble Space Telescope images, in two different filters, right? And this filter is for Hubble Space Telescope filters, the filter is F438 is the wavelength in nanometers, right? So this means 4,380 angstroms, 438 nanometers, and it's a wide band filter. Okay, so these are the two filters which we have. Okay, these are the two images which we have. We don't want these ones. We are going to just look at these two images. So I can click on these. I can click on this. Okay. Now what they've done in Must is that they've made it like a Amazon shopping thing, right? So whatever you want, you have to click on it, and you have to say you put this in the basket, right? So you can actually, like you were going shopping, you click on it, you put data products in a basket, and after you put it in a basket, then you can download it. So I can put it in this basket. I have chosen what I want. I put it in the basket, and you can see it's retrieving the data. And here you see there are two folders. One is HST folder, and this is HLA, right? And basically these are the two images which we are interested in. There is one with 555 nanometers, and this one is with 814. Now, if you look at these two images, there are three images. Essentially, the image which we are going to deal with is, we don't need this image and this image. We need the DRZ image, the drizzled image. Okay. So Hubble has a certain way of observing, which is called drizzled imaging. It's gone. Net is gone. Sorry? Yours. Mine I think is fine. Because I mean I can see it is. I'll just check whether it's working, but my net is fine. Yeah. Okay. Sorry. So we will look at this thing. I was basically showing you all this, right? So here the images which you are going to use are the drizzled images. So this is for M75. This is the drizzled image. You can see it's all described over here, the drizzled image for it for M75 in this filter 485.45. And here you have another one. This is the other image, which is with 814, right? This is for 81. So this is the size. This is for 555 nanometers. This is for 814 nanometers, right? So you'll do this and you'll click on download, right? I've already downloaded these images. So you can click on download and they'll download as a zip file, right? So basically what I was trying to show you is there are various sources from where you can actually get data, right? It's not just SDSS, it's not just HST, right? There are various sources from which you can actually get your data, right? It depends upon what are you working on. Supposing in this case I showed you some globular clusters, and in that case you actually have these things. I've given you the list of globular clusters, or I'll add it over here. Right. Okay. So this is a list of 11 globular clusters, right? Which also includes the one that did 5, 6, right? And these are all available in the Digital Sky Survey. So is repeat the procedure for any one of these targets, right? So use any of these targets and repeat what we did today for NGC 54666, right? 66, not 6. So please repeat the procedure. You can check on it. I have also written the steps for APT tool. So the first thing you need to do is do the more settings. Where you've set the model, the sky background, and the 0 point. Next step you're going to do is you're going to set the aperture, right? Then you'd say recompute photometry. There's a button over there. Check the list results, empty if the list results are there. Then you go to source list, right? Click on source list, process it to make your source list, right? And after that, you will list the results, export it, make the CVA, make the CSV file. For the G sources, you save the RA deck in for G-band sources, which we did, and then you rerun the whole thing with R-band, right? So you'll again do a rerun with R-band. Then TopCat, we can merge both these and do them together, right? So in case you get stuck about the steps which are being used for the APT tool, you can go through the steps which I've written over here, or you can also go through the video and see things. Like I told you, this time I'm doing level 1 and level 2 assignments for everyone, so that if there are people who are more enthusiastic to do more, which I would be very happy with, I don't want you to just repeat what I showed you. If you're enthusiastic to do something more, then I already showed you how to download HST data, right? So you can download HST data like the way I showed you and repeat the analysis for HST data, right? The only one big difference you will have to do with HST data is, I'll show it to you over here, is finding out of the 0 point, right? If you remember, I told you that for Sloan, you have to do 22.5, right? That's the thing for Sloan. But if you're doing it for HST, supposing you're doing it for 814, so then you'll have to write magnitude 0 point, right? For you can do for HST F814W. That's the filter, right? 22.5, you actually do this. So you look for this, and this is the Space Telescope site, and you can look for this. Depending on which instrument you've used, supposing you've used WIFPIC 2 data, you will use this. If you have used it, whichever data set you have used accordingly, you can see, choose your 0 point depending on what you did. Supposing you had, okay, these are the other filters, but there's 814. So 814, we're going to take for this. And accordingly, you will choose it. It came out of those things. Yeah, so you accordingly choose the filter and the instrument. If you remember, there were different instruments depending on the wide field camera 2, 3, 4, etc. You will accordingly choose your 0 point. So your 0 point can be whatever. So supposing if you've taken 814, right? See over here, this is 814. You may take this one depending on which camera you are using, right? So you need to do this correctly because the 0 point is what is important. It's specific to the instrument. You have to add the 0 point correction to HST data, or for whatever other data. Supposing if you're using with your own telescope, which you have at home, and you can use that also to make a catalog. In that case also, you will have to actually do this like that, right? So find out the 0 point, and accordingly you will run the whole thing and do it, right? So I will stop over here with this exercise of creating a catalog. Tomorrow we will make use of the catalog by making color magnitude diagrams. And before that, I'll actually do a slightly small theory class on what are color magnitude diagrams before we start plotting them, right? Today, many people have a little bit of a problem with APT, etc. So that's why I was in a hurry to do that. But you can give me your questions now, right? Bernadette, did you manage to plot everything? Did it work out fine? Okay, so thanks. There's a question. When do we use circular apertures and not elliptical ones? So typically when we are doing photometry for stars, then we always take circles because stars are considered to be circles, right? But generally, sometimes if you could be doing galaxies, right, or some elongated object for whatever reason, then you may take the aperture to be elliptical, right? So, so circular for stars and for galaxies, elliptical. That's the general guideline, right? Yeah. Are there any other questions? People with problems with APT tool, you can separately try to solve it and we can check it out. But let's see. Are there any other questions?
How many globular clusters have we been discussing today?
Yeah, we just did globular clusters create. Even tomorrow we'll be doing globular clusters. Tomorrow also we'll do globular clusters. We'll do HR diagram and we talk about some of the stars in globular clusters.
So you mentioned some Messier objects, no? Is it limited only to that or we are going beyond that?
No. You can do it for Messier as well as any other object you want. What I did is I basically showed you the procedure which you can follow for a certain object. But in principle, you can use the same procedure for any image, any astronomical image which you have of a catalog, of a cluster, a group of stars, or even a single star. You can use this method to find out their brightness and make a catalog. So you can use it for this thing.
Thank you.
Yeah, welcome. So YB, you are in Linux. Actually, in Linux, APT doesn't always work. It sometimes works, but it definitely does work in Windows. So later on, you can run the whole thing with Windows, and maybe that will just take. Maybe just a repeat of how to install APT on Windows. So I'll show it to you. You basically go to the APT website. Yeah, APT tool, Aperture Photometry. This is the website for APT tool, right? And directly from the website, there's a link, there's downloads. And if you click on downloads, You see over here, this is for Windows machine. So this is a zip file. So you just have to click on this, right? You click on this and I don't know why there seems to be some problem in this website, but I'm clicking on it. I don't know why it's not giving. But you'll click on this, download this, unzip the file, double click it, and it will install hopefully, right? So that's how you have to do that. I can see there's another question. Yesterday we were comparing planet properties with respect to Jupiter. Yes, because for exoplanets. Today we were trying to extract which property? So today we were trying to extract the magnitude or the measure of brightness of stars. So we are, if you see the catalog, we have their RA, we have the DEC, we have the brightness, which is magnitudes, and the error in magnitude, right? So that's what we are trying to do. We're trying to make catalogs of star clusters. Imtiaz, you're doing it on Windows. You unzipped your file and did you double click it and do it? Yes. Then what happens? Did it not create a file? APT. Okay. So Ajit Kumar is giving some suggestions. I am not using a Windows machine, but generally it works fine on Windows. Acha, okay. Okay, yeah. So somebody says that with Windows, it doesn't immediately start. You have to try it a couple of times before it starts. So you just do it. Imtiaz, Mohammed Imtiaz, you just have to do that a few times, and then it will probably work. Just try it. It finally will work. Can I use that? Yes. So somebody else is asking, can I use the same method to extract magnitudes for galaxies? Yes, you can do it using an elliptical aperture, but obviously the errors you will get will will obviously vary depending upon the kind of galaxy it is, right? If the galaxy is a smooth galaxy which has a smooth kind of brightness, then it is fine. But if the galaxy has other features, your errors may be larger. But in principle, if you want a rough estimate of magnitudes of galaxies, then you can definitely use APT tool. I use it myself for a rough estimate of galaxy magnitude. So you can use it. Yes, you can use it. Imtiaz, you can try it. If you don't get it, you let me know, but just try it. It will come. Yeah.
Madam, may I ask?
Yeah, please do.
Yeah. So yesterday we used TopCat, right? So where we have included the table and created the synthetic column, new synthetic column.
Yeah.
So once I have uploaded the table, loaded the table, I can create a new synthetic column. For the immediate next time, I couldn't get the, I couldn't replace the synthetic column based on the value correction, period value, right? So there is a error coming like dynamic variable can't have the formal parameters.
The same problem is happening with me too.
No. So what happened? You made the new column with TopCat, right?
Yeah, I have loaded
and
the
then
table.
You didn't save. You saved the file. Yeah.
Okay. So I need to save the file.
If you want to open it again later on, you should save the file, because otherwise this is just happening online. It's not going to save it. Okay. So what you do on TopCat does not get saved.
Mm-hmm.
You have to separately, I can show it to you. You have to, when you open TopCat, you have to separately press on file, and then you will say save table. And that's when you save the table. Only then it will get this extra column which you made. Otherwise, the extra column will be lost.
Okay. But
so you say
I'm
save
not,
table and then.
Yeah, I'm not opening again. I didn't close the TopCat. What I'm doing is, once I have created a synthetic column, so I made period value as 3.3. But that value didn't match, gave proper plot of the transport profile. So then I switched the value 3.25 something, but immediately it's showing the error like synthetic some dynamic.
What error is it showing?
The error is like,
what error is it showing?
Syntax error in synthetic column expression inverted quotes, that model
No, maybe you're doing a syntax error only, because you have to see, you have to put it mod, and here you will say call 1, right? And here you will put your period 3.24, supposing.
for the
this.
first time it's working. I mean, when I uploaded the table, I'm using, I created the synthetic column and it's working. But when I'm switching the value, 3.3 to 3.25 something, it's not working. Again, I have to discard the table and I'm reloading it. Then I'm using the value 3.25, it's working. For the first time, when I'm creating the new synthetic column, it's working.
Oh, I don't know. That sounds a little strange, because I've never had such a problem. I don't know. What kind of a system are you using?
I'm using Linux.
Okay. And so what is it? i3, i5?
You mean processor, right? It's I'm using a Ubuntu system, Ubuntu Linux.
Okay. Because one problem which does happen with TopCat is often the memory problem, right? That is the only issue which it has, sometimes which it has with memory.
Okay,
but otherwise,
i5. It is i5.
Okay, okay. So I don't know. I should check up with someone. Can you just send me a snapshot of the, email it to me? Email me a snapshot of that error message you're getting. Okay.
Sure. I will check.
You're sure that the syntax, you're sure the syntax is correct, no? You've put dots and
I
mean your whatever,
the syntax
brackets,
properly.
everything is correct, no? Brackets, comma, everything is correct. Okay, so just send me a snapshot, no? I can check with, I can even check with the person who has made TopCat. Why is this error coming?
Yeah, sure.
Okay. Thanks, fine. Okay. Yeah. But everybody will need to keep that TopCat running, because that's the one thing which we'll be using for most of the days. I'm a big TopCat fan, so we'll be using TopCat quite often. Keep it ready. Keep it on. Okay. Okay, so Bernadette, I had issues with my internet connection earlier, failed to hear you. Okay. Okay, fine. So you can have a look at the recording and let me know if you have some issues, right? Okay. So I will again, like I mailed to you yesterday, I will mail to you this PPT which I showed you all today, okay, with this list of clusters. I hope you can see it. Oh, the screen share is gone again. Right. So what I will do is I will send you all this PowerPoint, right, which has this list of these things. Like I told you, the assignment is to be either you repeat, the level 1 assignment is repeat what we did today with SDSS data, and the level 2 would be try your hand out with HST data and see if with HST data you can create a catalog of this kind, right? So we'll stop with that today. And tomorrow I'll continue with something. Actually, the PPT I want to send it tomorrow only, because I want to add it here, where we'll be doing using this catalog which we've got today. We'll use that to actually make what is called a color magnitude diagram. So I will do that today, right? So this list I can send it later. So see you. Thank you. Thanks for attending. And we will meet tomorrow. I can see, okay, there are 3 more messages. Okay, so that's from Mamta to you all about the assignment solutions. And I think I've already yesterday mentioned to someone a deadline of 30th of April. So as of now, that is the deadline. And but the ones who are, prompter, you can send it this thing. And yeah, if you need certificate of participation, etc. On the website also, there's a feedback form. It would be really very nice if you can fill the feedback form and pass it on to that, because we really want to know what do you feel about what's actually happening, right? Because this is taking a good amount of effort, but we want to know whether it's worth it up, whether what are people thinking about it, right? So see you all tomorrow. Mamta, do you want to say something? Yeah, where to send the assignment solutions? The same email ID where you're getting your mails from. I'll just cut, paste and put it over here. This is this one. The same, you know, you've been getting emails. I'll just this thing. IUWI. Okay, I'll just share it with you. Yeah, we can share that on Slack. Where do you have to send your thing?
Yeah, so I just want to be quick. So I think you people are enjoying very well Priya's sessions. It's always very wonderful, and I'm sure people like it and they learn a lot. So please send your assignment solutions of each day if you want certificate in the end, participation certificate. Send your feedback on the feedback form, which is also on the training program website. And it has to be done on the last day of the training program, not before. And of course, your feedbacks are important if we want to continue to conduct such kind of training programs in the future, because I see this is mostly meant for women researchers and students, but we equally support men researchers and men students, so there is no problem at all. Please feel free to join. But I now see that the enthusiasm has gone up to high school level. We don't only have early career researchers and master students and graduate students. We also start to have school students, and so I'm happy to see that's growing. It's very nice. I support it, so don't hesitate. But of course, it needs a lot of training from the person who is coordinating all these efforts, especially Priya in this case. So she has to start to now train high school students. So that's another thing. But send your feedback and let us know your motivation. Why do you want to attend such training sessions at high school level? It's getting curious, but at the same time, it is very good. So I support it. So please, and I'm sure even Priya encourages it. So,
Yeah.
So please send your assignments, because that's exactly when you will learn. I mean, you will benefit out of these sessions. It's only when you try it. And so I hope on the last day, we will manage to discuss a bit more about this training program and how much you enjoyed it. I'm sorry, I'm a bit sick this week, so I can't really talk to you much. So I'll hand over to Priya, and thank you.
Yeah. Thanks, Mamta. So yeah, I think we'll wind up with this and see you all tomorrow. Tomorrow we'll be continuing with stuff which we did today, but like I mentioned, in case you could not run APT tool or you had a problem with that, don't worry. The start of a file which you need for tomorrow, I will share that in the beginning of the session itself. And after that, we'll be just using TopCat. So you don't have to worry about APT tool. APT tool can be a little painful at times. So we'll be in this thing. So see you all tomorrow, but please do have your TopCat running. You definitely need that. Okay, so thanks a lot and bye-bye.